I like to start at the beginning so that nobody's left behind. It's kind of a funny term, space weather, because the space I'm talking about is outer space, and there's nothing out there except space. Weather is, well, if you think of it in terrestrial terms, you've got the wind, you've got the clouds, you've got precipitation in the form of rain and snow. Now, out in space, you can draw an analogy to some things that are going on out there that are of the same sort of meaning. And what that is we have the sun, we have the earth, we have the space in between, which is the space I'm talking about. And because of that relationship, we find that there is actually weather-like stuff going on between the sun and the earth. And why we should be concerned about that is simply because it affects the ionosphere. And the ionosphere affects HF communications. I mean, that's how we get around the world on HF. And without the ionosphere, we have nothing. So you'll get a feeling for what we mean by space weather as I explain the phenomena that are taking place on the sun and how they affect the earth and the ionosphere. So let's get into it. There's quite a lot of information in here. Back in March of 2012, there was a huge, I'll just call it an explosion because we haven't got into the terminology yet, on the sun. A solar flare is what it was called. It was extremely large. And it even attracted the media. They realized that this was being reported, and of course the end of the world might have been at hand. So this cartoon here was kind of a good one to start off with. You know, did the solar flare affect the electrical grid, GPS, satellites? Because sometimes it does. And in this case, the answer was no, 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 and no. So why are we worried about it? Well, we aren't too worried about it, but we do need to understand what happened with that solar flare as it affects our HF communications. And the reason it affects the HF communications is because the ionosphere is affected with these sort of activities on the sun. We have a disturbed ionosphere when things go wrong on the sun. So that flare was a class X 5.4, which is actually ginormous, as we'll see later on in the slides here. It's about as big as they get. And it's due to a solar storm. What that means is the sun is really active. It's doing all sorts of active things, and we refer to it as storming. So you're getting a feel for the space weather business. The reason this is important to us to know what's going on is because it's going to tell us how the ionosphere is going to behave or react to the storming or lack of storming on the sun, which in turn says, are we going to have a good day on HF, or is it just going to be a total waste of time? So I'm going to start from the beginning to try and introduce terms and phenomena so that those of you who aren't too familiar with this stuff will get a grasp of what's going on out there. So we'll start with HF propagation. Your classes, I think, may be reminiscent here when you think back to how it actually happens. Discovered something interesting tonight. We have these LED or LED pointers. They don't work on the screens. They disappear. So you'll have to use your imagination a bit, and I'll try and point these things out. So we have a little geometric diagram here of you at home. You're on HF, you broadcast a signal, goes up to the ionosphere. Now, just to get things right, the ionosphere does not reflect. It refracts. It bends. It bends the wave as it propagates through the ionosphere. So it's going up and it's bending as it goes through the ionosphere, and then it comes back down to Earth. That is not a reflection, that is a refraction. It's complicated, so we won't talk any more about it. Anyways, it comes down a long way away, and you've got a communication path. Now, the only reason this is done is because we have an ionosphere. If we didn't have the sun, we wouldn't have an ionosphere, but then we wouldn't be here either, so it doesn't matter. But the point is that the ionosphere is what makes all this possible. And it's the sun that makes that happen because of the ultraviolet radiation from the sun ionizes the air way up there. We're talking like 50 to 250 miles up. And it's that ionization. And ionization means that the ultraviolet radiation is very energetic, and it can actually strip electrons off of the oxygen and nitrogen molecules that are in the air. I mean, we're not, what is it, 80% nitrogen, 20% oxygen roughly. Anyways, the energy up there strips the electrons off, and it forms a layer called the ionosphere because it's ionized. And it consists of free electrons just drifting around like clouds. So, the density, the number of electrons that are actually floating around up there has a great deal to do with whether the ionosphere is going to be nice and refractive and give us lots of long-distance communication, or whether it's not highly ionized, which means the ionosphere is not going to behave too well and we're not going to work any DX around the world, maybe just North America, and that doesn't count. Anyways, get the idea that the ionosphere there has free electrons floating around caused by the ultraviolet radiation from the sun. Now, there's a thing called the sunspot cycle. I think probably everybody's heard of that, whether you're ham or not. This is an 11-year cycle that the sun goes through. It allows us to enjoy really good propagation when the cycle reaches a peak. And when it reaches a low, the propagation isn't much to write home about. Pretty boring. HF is kind of not so much fun. So this cycle that the sun goes through, we pay a lot of attention to that. Some of us who are keen look forward to when the next cycle is going to peak. And when it peaks, it means we're going to get good ionization, going to get good DX, good communications, reliable, stable, and so on. On the other hand, when the sunspots disappear, at the minimum, band conditions are poor. So, we'll see more about the sunspot cycle and what sunspots actually are. The propagation variables. You know, you have to imagine the ionosphere is not just a steady layer of ionization. It's anything but. It's like looking up in the sky and you look at clouds. Sometimes you get a strong overcast. That might be equivalent to saying, the ionization is strong, uniform. That's really perfect. On the other hand, you look up and there's clouds drifting around. The ionosphere does the same thing. It's not homogeneous. It's irregular. It's bumpy. It's got holes in it, and so on and so forth. These are the sort of things that make HF operations kind of neat because you never quite know what you're in for, good or bad. But because of this highly variable radiation and the way the ionosphere moves around, we have things called openings where, oh gee whiz, I can hear a DX station way over in Africa, and a half hour later it's gone. Where did it go? Why did it go away? Why did we hear it in the first place? Now, you also have a day-night variation. The reason for that is that always half the planet's illuminated by the sun, so the air is getting ionized, but on the night side, it's not getting ionized. In fact, it's deionizing. The ionosphere is losing its ability to refract signals on the night side. Seasonal variation. Well, you know, in summer, the northern hemisphere has got more radiation on it than the southern hemisphere. So you might say that summer's better than winter, but maybe not. It's over-ionized. And that's not good either. If you have over-ionized ionosphere, you get too much absorption. Yearly variation. We don't have a circular orbit around the sun. It's elliptic. There is some variation there, and so on. That's saying nothing about the sun. This is just what goes on Earth. You know, those of us who muck around on the bands, you know, sudden loss of path, signal's there, 10 minutes later it's gone. So it's unpredictable. I think Keith was telling me, I've forgotten who it was, a good DX station that was in there for a while and then it's gone again. Unexpected openings. Sometimes the band is wide open, meaning you're hearing more than you know what to do with, and other times you don't hear anything. So paths, we call them paths. The ability to get from one place to another is the path. And is the path there or is it not? And it always depends on the state of the ionosphere, which is a highly variable entity. So if we're going to understand how the ionosphere changes, how we can relate that to propagation variances or variables, we have some help. There is predictive software. There is a science behind this now. It helps explain what we hear and what we don't hear and when we hear it and why we don't hear it. It's good for operating skills. If you get an understanding of what's going on, you can probably use your time more valuably than just hanging around waiting for something to happen. And in order to understand how that works, we have to understand what is going on the sun. Because when you look at propagation reports online, they're always going to be talking about the sun, things we measure on Earth about the sun. And it's also interesting to see what, in fact, is actually going on the sun. It's pretty interesting, scary stuff, actually. So the sun is the driver. The sun determines how successful or unsuccessful we are going to be with HF propagation. So I got 3 sun symbols there. The glum one is like the solar minimum, where nothing much is going on. The one in the middle is sort of halfway up the cycle where things are starting to get interesting. And the one at the bottom there is when things get really interesting, because the sun now becomes what we call stormy and unpredictable. So we have a quiet sun, that's at the minimum. We have an active sun, which is somewhere in the middle. And then we have a stormy sun, which is at the peak of the cycle, which is always rather interesting. And the ionosphere tracks that behavior. Okay, solar emissions. The sun, of course, we know it supplies us with warmth and light, good thing. The other thing it does is it radiates a huge amount of ultraviolet. That's the stuff that gives us a sunburn, but I mean, there's a broad band of ultraviolet which goes from maybe not being too dangerous to being deadly. Thank God the ionosphere is there, because it protects us from that, or I should say the atmosphere is there. And the UV creates the ionosphere, which protects us from dangerous, deadly radiation. X-rays, same thing. Sun emits X-rays. The sun has a magnetic field, and sometimes well, all the time we're bathed in the sun's magnetic field. It just goes out into the planetary system, our solar system. So we're immersed in that, whether we like it or not. And sometimes we get ejections of the magnetic field coming from the sun towards, well, any direction, but if it's towards us, that causes more complications. And we'll see how that works or doesn't work. So the number of occurrences and the intensity of all these variables depends on where we are in the solar cycle. We happen to be more or less at the peak of cycle number 24, and we'll see some graphs of that later on. Just so you know, if something blows up on the sun, the electromagnetic radiation from that, like the light, takes about 8 minutes to get here. So when we see a bright light on the sun, which is something that's erupted, that happened 8 minutes ago. Trivial. Anyways, all of these things have significant effect on the ionosphere. So now you're getting a feel for maybe why we call it space weather. The space is in between the sun and Earth. It's a vacuum, but it's not empty. I'm not talking about dust or rocks or things like that. I'm talking about electromagnetic radiation. I'm talking about particles that are emitted from the sun, which are like clouds. The wind, there's a thing called the solar wind, which is blowing this stuff our way all the time. So there's the wind. So we have a solar wind. We have clouds, which is solar mass that's being boiled off and heading towards us or somewhere else. And precipitation refers to charged particles like electrons and protons and things that are streaming out from the sun in all directions. So that's where the term space weather comes from. Boring statistics. The sun, believe it or not, is a yellow dwarf. The hydrogen is being converted to helium, in an atomic fusion reaction, which supplies all the heat and light. And 1% is other stuff. It's a nuclear fusion reaction. Two hydrogen atoms are under great pressure and temperature fused together to make one helium atom. Said energy equals mc squared, which means the energy released when you put these things together is not quite twice the mass. Like if hydrogen weighed 1 pound and you put two of them together, you'd think you get 2 pounds of helium, but you don't, you get 1.9 pounds. The missing mass is energy. That's just the way it works. And it's multiply that times the square of light, and that's a big number. It means a lot of energy is released. It releases 384.6 yottawatts. I bet you never heard of those before. That's a lot. 10 to the 26. That's 10 with 26 zeros behind it. That's a lot of power. The middle of the sun runs at 13 million degrees Kelvin. The surface temperature is quite cool at about 6,000 degrees. So this thing is hot. I mean, it is hot. And that heat, of course, makes sure that there's no such thing as a regular, ordinary atom of helium or hydrogen. Everything is boiled apart, so you're just left with particles stewing inside this huge ball of hydrogen. And of course, because it's so darn hot, it radiates electromagnetic energy across the whole spectrum. I mean, that includes heat, infrared, includes visible light, it includes ultraviolet, and so on it goes. Just so you know, that's the sun, that's the Earth. It gives you an idea of the magnitude of the size of things out there. The sun is a big place. It's a good thing it's 93 odd million miles away. What is it made of? It's not a solid, it's not a liquid, and it's not a gas. Those are sort of the three states of matter that we commonly run across. But when you heat stuff up to the temperatures of those ones we just talked about, you get a plasma. And the plasma is the fourth state of energy, which is uncommon in our everyday business. It's just an ionized gas. It usually means it is hugely hot, and there's no such thing as a molecule or an atom. It's all just particles stewing around for whatever reason. And in the sun, the reason is because of the density and the weight crushes everything towards the center. It heats up, starts a fusion reaction, generates more heat, and so on. There's actually a structure to the sun. Not that we need to know an awful lot about it. One thing I always used to wonder about is, well, where's the surface of the sun? It's not a solid, it's not a liquid. You can't stand on it. If you ignored temperature, could you stand on it? You know, no, is there any solid ground up there? And the answer is no. It's a plasma. So when you look at the sun, you see a surface, but what is that surface? Well, it happens to be the surface where photons, that means the heat and the light and all the radiation from it, can actually be seen. You can't see it any further in because of the density and the temperature. The photons in there take up to 1 million years to get from the inside to the visible surface of the sun because of the shortness of the mean free path, as they call it. Like, take a photon trying to get out of a density beyond comprehension. There's nowhere to move, even if it's there. And if it does try to move, it hits something else. For a photon then to move from the middle of the sun to the surface takes up to that. Now, that's a calculation. Nobody's gone there to measure that, of course, but it's I looked at the calculation and the assumptions, so I just thought that's kind of interesting. The solar wind, there's the first piece of space weather. 7 billion tons of electrons and protons are expelled from the surface of the sun per hour, and it's lost to space. It just boils outwards. It's gone. And that's what the clouds are all about. The solar wind, those clouds. The clouds are made of electrons and protons. They tend not to recombine like you think they might because the temperature of those particles is so high that they simply don't get together. And here's something that nobody seems to have an answer to. The corona, which is outside of the surface a bit, or quite a lot, is actually 1.5 million degrees, which is hotter than the actual photosphere, which you see. The photosphere is something like 6,000 degrees, and all of a sudden the temperature rises to 1.5 million degrees for reasons unknown. And that accelerates the loss of mass and particles and everything just blows off the surface of the sun at a huge velocity of anywhere from 300 to 750 kilometers per second. So if something comes off the surface of the sun, it takes about 2 days for it to get here, because it's not going as fast as light, obviously, but it's covering 93 million miles in, a couple of days. That's pretty fast. We do pay attention to that because you will see on the sun that something's gone on. 8 minutes before that, there was the so-called explosion, which means the electromagnetic energy has arrived. What you might see is a portion of the sun has got blown off, and it's headed somewhere. And we'll see some photos of that, actually. Yeah, flares are, that's the kind of thing that launches this stuff. But we got things to look at here that shows you what a flare looks like, why it's there, and so on. So, again, these are things that impact the ionosphere significantly. If you collide with one of these great clouds, it causes extreme problems. As I mentioned, the sun does have a magnetic field. There's a very beautiful looking uniform magnetic field. It's the last time you're going to see one of those in this talk. You'll understand what I'm talking about shortly. Why is there a magnetic field? Well, I think that's open to debate, but the thing is there are currents circulating for whatever reason in the Earth and even in the sun. And it's a combination between circulating currents and the magnetic field. It will generate, the circulating currents in a conductor will generate a magnetic field, which is what's going on inside the sun somewhere down in there somehow, and also within planet Earth. So this is really important. Well, it's all important, but this is kind of really interesting too. So it's got a magnetic field. So the sun rotates. It goes around one rotation on its axis. Depends which part of the sun you're looking at. Because it's not a solid, rigid ball like the Earth. I mean, on Earth, everything goes around in 24 hours. Well, on the sun, it takes about 25 days for the equator to go around, but 34 days for the pole. The reason is it's not solid. It's a plasma. It's rotating at different speeds. The equator has a long way to go, but it's rotating at a different speed than the pole, which takes shorter days to go around. So this is kind of interesting. The bottom line on this as to why that happens is just because it's more like a liquid than a solid, is that it distorts the sun's magnetic field. I mean, our field was nicely arranged back there. It's all very uniform, predictable, looks nice. That's not what happens in the sun. If you look at these three diagrams, here's the sun at the minimum of its sunspot cycle. It's got a magnetic field which is well behaved. Goes to the North Pole, around to the South Pole, just like Earth. But because it's rotating at different speeds depending on the latitude, the field gets pulled. It starts to rotate in the sun as well. And over the years, say 5 years, the magnetic field gets wound up inside the sun. It's like this leading edge here is going around and winding up more and more of the magnetic field structure inside the sun. Kind of like a rubber band, yes. Well, you'll notice these little things here where you can see something about the magnetic field comes out of the surface of the sun and goes back in again. This is where the magnetic field inside erupts through the surface, goes out into the atmosphere of the sun, if you want to think of it that way, and then back in again. And the more this field gets wrapped up, the more you see these bursts out of these sunspots. These are the sunspots. That's what sunspots are. As the sunspots become more and more apparent on the surface of the sun, it's because the magnetic field is getting wound up and is bursting out over more places from the interior of the sun to the exterior of the sun. So they're like magnetic holes, if you want to think of it, where the magnetic field is escaping. Now, because the sunspot cycle has an 11-year cycle, this thing gets wrapped up so tight that for some reason it fails. The magnetic field begins to collapse, deteriorate, the spots disappear, and 11 years later, a new magnetic field structure in the sun appears, and it's of opposite polarity. It's reversed. Now, how that all happens, I'm not the guy to tell you that. This is what does happen, or at least that's the theory, and it looks pretty good. So, if you were to look at the sun just in white light, start of the cycle, there's no sunspots. The magnetic field is nicely structured inside there. Maybe 4 or 5 years later, sunspots start to appear. This is where the magnetic field is rupturing out of the sun into these great loops. When you get into the peak of the cycle, more spots, bigger spots. That's an airplane. They must have flown in front of the sun when they were taking this picture. So I thought that was a good thing to include. But that's more spots as opposed to no spots. Minimums, solar minimum, solar maximum, as it's called. Now, a measure of how active the sun is, in other words, we're calling the sun going from inactive when there's no spots to being really active when there's lots of spots. So there are ways that you can count the sunspots that appear, and the number of sunspots is a direct correlation to the activity on the sun. So there's a thing called the sunspot number, which you'll see in propagation reports or solar reports. And the number can be as low as 0, meaning at the solar minimum there's nothing going on, the sun is very quiet, to maybe up to 180, or if it's extraordinary, maybe 200, which means the sun is really, really stormy. And the idea is that by counting sunspots and assigning a sunspot number, you can get a feel for what the state the ionosphere is in. So here's a historical representation of the sunspots from the first time that somebody looked at the sun, which would be Galileo in the late 1600s. I don't know how they did it without losing their eyesight, but nevertheless, I guess they had smoked glass in those days. So they were looking at sunspots and doing a count. That's how it started. They'd count the sunspots. Now this is kind of interesting here. There were no sunspots observed between about 1650 and 1725. That's the famous Maunder minimum. You hear people talk about, oh, the Maunder minimum. Then you hear them say, well, that was when they had the Little Ice Age. There's a direct correlation in time. I don't know if there's any other correlation, but that's when the Little Ice Age occurred. The sunspots disappeared, and there was a Little Ice Age. You can draw your own conclusions. Coincidence? Who knows? Anyways, things picked up again. And you can see the sunspot numbers vary, which means the sun's activity is not stable. It's up and down. It's all over the map. Part of our task is to try and predict what's going to happen next time, the next cycle. And it goes like this, and it goes like this. And this was a terrific cycle out here. And yes, it was. I got my license sometime in here, and I just thought ham radio was like that all the time, everywhere, all day long. Surprise! The late 50s. There would be this one here. Unbelievable. Auroras in Victoria. I grew up in Victoria. And the auroras that I saw there were just astounding. I went outside at night and watched these things in the clear sky. I've never seen it since. I dare say I heard them. People say they can hear the aurora. I believe them because I think I did too, but I couldn't hear anything. It just like a hearing sound. So God knows what was going on. Anyhow, we're getting down here into the last few cycles. We're in cycle 24. And when I did this first, it was in March of 2012 when we were supposed to be about here on the cycle. This was the prediction. Although there's been a concern lately that we're ramping down in terms of solar cycles, like this one. This is lower. This is would be lower, and 25, the next one, should be a very dismal. So there is concern that something's going on with the sun. I could speak a little more about that after the lecture, but this stuff, predicting it, is kind of interesting. Anyhow, that's what it looked like back then. Here's, again, in March of 2012, is a plot of the smooth sunspot cycle. It's very ragged here simply because they're looking at spots one day that don't exist in the next day or week or month. But if you average them out, this was cycle 23 that was ramping down. And back then in 2012, we were on this part of the cycle here. This was the prediction. Quite a bit less than cycle 23. So this was dismal. Those of us who do HF were really not very happy, because lower activity means poorer ionospheric conditions for HF. Anyhow, we can't do anything about it. So here's what's actually happened. This was the original prediction. This is where we are today. Now the interesting thing is, we got a twin peak. It's peaked twice, and the second peak was stronger than the first peak. That sort of thing happened back here on cycle 23. People said, we had a double peak. And I remember that because it was really good. You basically had good propagation conditions for a couple of years, which was much longer than you normally. And same here. We've had good propagation for 1, 2, 3, going into 4 years now, because this peak is broad and has a double effect to it. Now, it's not as strong as here, but it's awfully damn good. So much for the predictions. Sunspot numbers were better than expected. The second peak showed up out of nowhere. So it's been stronger and longer, and continued good propagation. So back to the sunspots. That's what they look like up close. They're eruptions where I've said the magnetic field will be coming out of one of these here, and it'll be going back into its mate here. Be another set here that are somehow coupled to each pairs, where you have the magnetic field coming out of it. It looks dark because it's cooler. So there's a magnetic field coming out of here and going back in there. So that's what the sunspots are all about. And the more sunspots you see, the more are escaping, which indicates more activity, which indicates all sorts of interesting phenomena. This is just a diagram to show what the sunspot structure looks like. You have the magnetic field that's all twisted up, as we saw earlier from the rotational. And it bursts through the surface, and all the magnetic lines of force are up there, and they go back inside. So that's what's going on with the sunspots. That's what you see, or is what you will see shortly. I just have to point something out here. There's a little bit of physics. I know you're all familiar with it. Wherever you have a magnetic field and you have a charged particle like an electron or a proton, if it's moving, it moves in a spiral fashion around the magnetic line of force. It's captured by that. Okay, so it's just good enough to know that when you have on the sun, as we'll see, a magnetic field, you'll have particles that are trapped in the magnetic field. This is a basic physics property. And there you see it. There's a couple of sunspots. You have the field emerging here and going in there. Now, normally you wouldn't see a magnetic field. I mean, it's invisible. But what you do see is all those particles that are trapped on the magnetic lines of force, which are hot and glowing. And so you get a beautiful picture of the magnetic lines of force just by looking at these basically photographs. So that there's the magnetic field coming out and going back in. Again, look at the sun in ordinary white light. You see sunspots, not much detail. It looks pretty boring. But that's measured at visible wavelength. That's what we would see with our eye if we looked at it. But what if you look at other parts of the spectrum? That's what the sun looks like at other frequencies in the electromagnetic spectrum. This is all above visible light. And yeah, it all looks the same, but it's much more apparent. The devices that detect all these different bands of illumination show different features and details, although you can certainly see that these are all the same. This is hugely intense. Temperature is high, temperature is lower down here. So higher temperatures are going to appear brighter, more emissions, and so on. Now just have a look at these. Is there anything about those that look the same? Is there a feature on there that makes any sense that you could point out? I feel good about this. I can stand up here as a professor or whatever you want to call me, or a nutball, you know, and that I would be in the class and the professor would say, well, what's the commonality here? And I'm going, duh, you know, I don't know. Well, don't worry about it. That's the commonality. These are bands above and below the equator. The spots are arranged along a band, right? Band, 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 band. Those bands are where the magnetic field in its wrapped around features is, I suppose, weakest or something, but that's where it's erupting. And what you see at the start of the solar cycle, when sunspots start to first appear, is the bands are high. There's a high band up here where you see the odd spot, a band down there where you see an odd spot. And these bands move this way as the cycle progresses. And when they get to the equator, that's when you've hit the peak and the sun's magnetic field starts to collapse. So just by looking at it, looking at these photos, which you can see on the web anywhere you go for solar, you'll see those bands. Well, as we saw, those are the eruptions out of the sunspots. Now I'm going to try this, and I don't know if it's going to work. It didn't work a while ago. It may not work now. No, I can tell it's not going to work. Anyway, well, I'll just click on this. Yeah. No. It's not going to work. So let me just bring it up again. We can look at the static picture here. You can see how the eruption out of this spot has that huge arc going back down into the sunspot. I mean, that's what it looks like. And that is enormous. When you look at the size of the sun, that's big compared to the size of the sun. And when you measure the size of the Earth was somewhere down a layer like that, it gives you an idea that this is pretty big stuff. Okay, so that's a solar flare. What you just saw was a solar flare. In other words, it was an eruption on the surface of the sun. If that movie had worked, you would have seen it just come bursting out of the surface of the sun like that and go back inside. And enormous amounts of energy are released, obviously, 10 to the 25th joules. That's a lot. I don't know how much that is. But it's a lot. 15% of the sun's total energy per second lasts from seconds to minutes. And this is what happens when you get a flare. Like, one of those things erupts. Huge amount of energy is released. A great pulse of electromagnetic energy is released. If you were looking at the sun and you saw it, you'd see this bright, hugely bright flash of visible light. And 8 minutes before, this is all what's happened. But then there would be electromagnetic emissions through the radio spectrum and then through the X-ray and all the rest of it. It just releases energy in every form that you can imagine. And of course, it has a serious effect on the ionosphere. Now, this is a theory about what happens. You see the looping magnetic field goes up, but for instance, this loop here may decide to reconnect here, like it's done. And if enough of that goes on, the loop actually breaks free from the surface of the sun. It's got a contained magnetic field in it. It's actually a mass that's being flung off the surface of the sun out of that great arch and contains its own magnetic field, and it flies off into space. Now, normally we don't care about that unless it happens to be coming in our direction. When you look at propagation forecasts, they actually rate these flares according to energy. Class A, B, and C happen all the time. They're nothing to write home about. Quiet sun. Active sun, you'd see class Cs. Stormy, like right now, we're in the stormy session. We'll see class X flares. One happened not very long ago, maybe 2 weeks ago. It was a major one, but we didn't notice anything different except if you happen to be operating, probably the band went dead. Again, when one of these things goes off, this is a graph of the X-ray emissions monitored by a couple of satellites that's their job in life, is to monitor radiation from the sun. And you can see that here, nothing much happened, and then all of a sudden, you got this huge rise from about 10 to the minus 9th to 10 to the minus 4. That's 5 orders of magnitude increase in the X-ray flux inside of an hour or so. That's not good. When you're operating like on a contest, I have this graph running in real time. It's real easy to find it. In fact, if you go down to this link here, you'll find all this stuff. And all of a sudden, what was a packed band, you begin to think, where's everybody gone? It's dead quiet. You call CQ, nobody answers, and yet 15 minutes ago, you couldn't find a clear frequency. It's because you had a flare. The sun flared, released a huge amount of electromagnetic energy, over-ionized the ionosphere, signals were simply absorbed. So you see there's a bit of a balance here. If you don't have enough ionization, your signals don't go anywhere. And if you have too much ionization, they don't go anywhere either because they're absorbed. So you can't win. You got to find that window of operating opportunity, I suppose. Anyways, there's something called a coronal mass ejection. That's when that flare that went up like that, closed on its magnetic field, was cut free from the surface of the sun, and off it went. There's a chunk of it going off there. Let's see if this works. Watch this. Watch. Oops, there it goes. Holy cow. Some of the material falling back down on the surface here, the little bright spots where it comes back and impacts the sun. Where there's a whole pile of it that just went off in that direction. Now that's not just a few miles across. That could be hundreds of thousands of miles across. It's just have another look at that. I mean, that's a zillion times the size of the Earth. We're just, unimaginable energy and power. Oh, I don't know what the real time scale would be. But when those things go off, they are probably measured in minutes. But for the actual whole thing to develop and disappear might be in the order of an hour or two. With remnants, I mean, it doesn't just suddenly stop. It takes a while, maybe hours to. So these things are quite sudden, as you saw in that. Oh yeah, what do we got here? More stuff going on. It's a nasty place. I mean, look at that loop. Pow! Oh, there it goes. That's lost mass. It's got a magnetic field in it. It's got charged particles in it, and it's going that way at 700 or 800 kilometers per second.
What happens when that arrives at the space station?
Well, they get worried. Yeah. I mean, that's one of the problems is shielding of the astronauts inside space vehicles because of the dangerous levels of radiation that are up there. It's not so much that it's not like a whole chunk of mass comes and goes clunk, because it's all just particles. It's particulate, negative and positive charges, which are not good for any of the electronics or any of the people. It's ionizing radiation, is what it is. Oh yeah, in fact, if it's intense enough, you'll die immediately, which is what that stuff is out there. It's hugely dangerous. Yes. Oh, we're getting ahead of ourselves here. Well, that's not too bad. I got a better one, though, I think. Let me just have a look here. Let's try this one. Yeah, that's a little, oops, that's a little clearer. Nope, this way. Up. All right, we'll get it back again. Yeah, what this is a, well, what they do is they put a disc here so you block out the light from the sun, which would otherwise blind you, at least the telescope that's looking at it. So from this you can see, that's the sun there, this is the blocking disc, but you can see what's coming off the sun there in real time. And so now you get a better understanding of what the solar wind is all about and why the space in between the sun and the earth is full of stuff. Electromagnetic stuff, particle stuff, solar mass. You know, if we happen to be Earth here, ooh, right there, we would know about it. And may as well just turn the radio off for a while. All right. Come on. There we go. All right. So with one of those CMEs, they call them CME, coronal mass ejections, the simplified diagram shows that mass, or just the solar wind. You just take the solar wind, which has the sun's magnetic field associated with it, coming out as the wind, impacting the earth. And instead of the earth having that nice, beautiful, symmetrical, well-organized pattern, it's all squashed to heck. The force, we'll say, of that wind is not insignificant. It distorts the magnetic field tremendously. It crushes it on the sunward side and stretches it out on the dark side. Now, we'll see in part 2. This is a 2-part series. Part 2 talks about the effect of this on the earth. In other words, all this stuff that's going on the sun, when it gets here, what happens. So we'll see about that in part 2, which is going to be 1 month from now, first meeting in February unless someone changes the schedule. But this CME, everybody takes notice if there's a CME forecast, and if it says headed towards Earth, that means that ionospheric conditions are going to be quite interesting, whatever interesting really means. Not an everyday event. There is yet another effect on the sun called a coronal hole. This is, well, let's take a look at it. There's the sun. These dark patches are coronal holes. It means that instead of the magnetic field coming out and going back in, it just comes out. It just goes out into the solar system, interplanetary space. That kind of forms a highway upon which all the particles that we're talking about here getting boiled off the sun arrange themselves around the magnetic lines. And so this is like a highway of particles. It's just, massive particle movement out from the sun, out from here, out from there. But since we're looking at the sun this way, that stuff isn't probably going to come towards Earth. But if Earth gets in line with a coronal hole, it means that we're in that magnetic path highway where more particles from the sun are going to be impacting the Earth and the ionosphere. So when somebody says, oh, there's a coronal hole, that's what they're talking about, and that's not a good sign. So kind of just to sum things up here, it's an 11-year cycle, 10, 11, 12, it's, give or take. There's the quiet sun, 1996, not much going on, minimum of the solar cycle. Here it is in 98 when it's active. You can see there's the line of sunspots, but they're fairly high latitudes. They're not down here or down there. Here you can see them again, and there are more of them, and they're getting closer to the equator, indicating that the cycle is moving on. And since we'll be posting this on the web, you can read through all the detail, but things are pretty quiet there in terms of HF radio. Things start to get interesting when it's active, and when at the peak, we don't know what to expect, but it can be really interesting sometimes. It's good stuff. Summary, well, sunspot cycle drives ionospheric conditions. and our abilities to communicate on HF. The solar wind carries all these particles out. That's the wind. The particles are the clouds. And in fact, the particles are the precipitation, because when they arrive at planet Earth, they come out and down onto the magnetic field in the Earth, as we'll see next year. So they precipitate out of the solar wind. So that's probably all you need to know. Is that enough, or do you want more? No. So you get the solar flares. The solar flares are the things that produce all the X-rays, and the mass ejections and the coronal holes. Those are the three things that bother us most. The rest of the time, it's just standard radiation from the sun. You can have a look at this website here when we post it. It's really good for showing all these pictures, forecasting what's going on the sun, how it's going to impact Earth, and so on. And this is a bit of a movie where you can watch more about what we've just talked about. So, as I said,
Can we go back to that last slide just a second? That first link you got, www.swp.
yeah, Software Prediction Center, I think it is, swpc.noaa.gov/communities. Yeah, it'll probably show up better on the slide when you download it, if anyone ever does. Yeah, so, oops. So February 1st, or 5th, I think it is the first Thursday, we'll look at what those things actually do to the ionosphere. So we get sudden ionospheric disturbances, we get blackouts, we get geomagnetic storms. These are all different classifications as to what goes on up there when the sun is not behaving itself. Many of us know, or at least we are familiar with the A index and the K index and the solar flux index. These are common parameters that are published that give people who have some idea what they mean. This is what we'll talk about, so you know what it means. Give you a good idea what's going on and whether it's a waste of time to put the radio on or not. Talk about auroras, because they're part of this whole thing. And you can visit this web page, which is also a very good reference summary for propagation conditions and what's going on. George?
You have that slide there with the historical cycles.
Yes. Yes.
Going back to the 1600s.
Yeah.
Did somebody actually measure that back in those days somehow?
Yeah, they counted the spots.
Why did they care? They didn't have radio.
Well, these guys are like Galileo. Why did they care about anything? It wasn't your average citizen who was concerned about this at all, but you know how it is. There's geeks then, there's geeks now.
You had a way to measure that.
Some poor apprentice in that probably had
Yeah, I couldn't.
Define them for groups, for size and groups.
Well, yeah, the definition and the science of counting sunspots is pretty complex. I don't quite know how you do that, because, as Jan says, they occur in complexes, not just a nice single group, but you know, there's all of them all around. Is that one sunspot, or is that 6 sunspots? Or so there's a methodology to it, and if you have a career in that, that's probably going to be a pretty boring life.
Doesn't the pinhole camera show sunspots? It doesn't require anything particularly exotic.
You're probably right. Yeah, pinholes. Yeah. If you want to try, I wouldn't recommend trying to look at sunspots directly. No. Yeah. Yeah, I have a telescope which has a sun filter in it, and I could look at the sunspots a long time ago. I haven't bothered for about 30 years. Seen one, you've seen them all.
You ever heard about the Hyder flare?
No.
There was apparently in the 17th century, or 18th.
Oh.
Yeah, there was a flare that was so strong.
Mm.
And that was just when they were putting in all the telegraph lines.
Yes.
And apparently it created so much energy, light that flew off the...
Well, what happens there is you have a ginormous antenna, right? I mean, you got these wires strung for 1,000 or 2,000 miles across the surface of the Earth. You have one of these flares impacting energetic particles. There's an induction into the wire. A current flows because you've disturbed not only the ionosphere but the Earth's magnetic field. It fluctuates. It changes. In a changing field, you got long conductors like power lines, all the high tension lines. A current is induced into them. Now people talk about, oh, we're going to have a blackout and everything's going to blow up, and you know, the transformers, they show on movies, you know, the transformers all blow up. The reason is that they have problems is it's DC. And these transmission lines aren't designed for DC currents, they're designed for AC, and the transformers don't like DC. You plug a DC current through a transformer, and the transformer is going to be very upset very quickly. That's why they put, you know, fast-acting circuit breakers in, such that if you get an event like that where you get a DC current flowing in an AC circuit, which you don't want, the breakers open up, and so the lights go out. But it's a protective relaying system that's intended to save things like transformers.
Yeah, pipelines.
Oh, pipelines have the same problem, yeah. Good conductors, even if they're buried a little deep in the, yeah, whatever. Is that it? Oh, yeah, Barry.
How many more cycles have we got before the sun's energy gives up?
How many cycles? Well, take maybe,
5 billion divided by 11 years.
yes, that's right. That's about right. I'd say so, give or take, you know.
So we're good then for the next year or two.
Well, just to add a little footnote, at the BCDX convention, one of our guest speakers was Dr. Ken Tapping from the Penticton Radio Observatory. He's a solar scientist. And I mentioned solar flux there, that SFI index. He measures that. He built the radio telescope that measures that. It's used worldwide. It's a worldwide parameter. Other telescopes in the world do it, but his is one of the most well-known. Anyways, he came up and he said, what's going on? Well, he gave a talk on what's going on with the sun. You know, up until a few years ago, they basically thought they had it aced in terms of understanding the solar cycle and the activity that goes on and the flaring and so on. That's not the case anymore. That trend you saw with the 3 cycles going down and the 4th one not looking much good at all seems to be related to a fact that the solar flux, which is classically related to the sunspot number. Remember the sunspot numbers? You count the number of sunspots. You can graph that, and you can determine from that graph what the solar flux is. Now, the solar flux is the electromagnetic energy that's coming down. Rather than counting sunspots, you actually measure the electromagnetic energy coming down from the sun. And it's correlated very well. It's a bit of a scatter diagram, but it correlates and has done for years, decades, many, many cycles. But the last 2 or 3 cycles, the correlation is disappearing. And he showed the scatter diagram instead of just being a sort of a cloud. It's got these lines that go way outside they just shouldn't be there, which means that the sunspot number and the solar flux index aren't correlating anymore. Well, guys like him get really worried about that. And I'm kind of concerned too, although I don't know if I'll be around for the next cycle, 10, 15 years away. But yeah, so I haven't got it figured out. It's interesting.
We're good.
Yeah, you young guys, you got a chance. One more cycle, Barry, that's it for us maybe. Well, I'll speak for myself. If you want.
Actually, it was on 10 meters last week at
Yeah.
the Richie contest.
Yeah,
The screen was just full of
Yeah.
contacts, just solid across.
yeah.
See them there?
Yeah, and that shouldn't have happened. That shouldn't have happened. You know, because we're past the peak, but you saw that second hump in the graph there where it went and then it's back up again. Yeah, we're enjoying more than we did a year ago. Very odd.
Well, and also leading into the solar max, it was so dead
Yeah,
for so long. Like
it was.
2009, 2010.
Yeah.
Terrible, like 60.
Yeah, that was the other anomaly, was the solar minimum was much longer by a year, maybe. It went on for it seemed like it went on forever, but it was longer than normal. It was not it was a slow, and it's hard to get back up the line, climb up yeah, anyways. Is that it?
Any comment on the sun's conveyor belt?
Which one would that be?
Well, no, they say the speed, the underlying convection.
Well, yeah, I've seen cross sections of it. It's very, very complicated. How do you get the heat out of the middle to the surface? And huge convection currents in the plasma. How is it organized? How does it correlate with the magnetic field? I don't understand it. But the thing is, the heat has to get from the fusion reaction in the core out to keep it stable. I mean, you can't have the sun suddenly heating up or cooling down. That would cause further problems. Yeah.
Yeah, because they made comments with respect to the conveyor belt slowing down. with respect to the weather, because our 11-year solar cycle is also in the tree rings and
Oh, yeah.
nature and all that.
Yeah, they've correlated it to that sort of thing, but no, I don't know. Very difficult to see what's going on inside the sun. That's the problem. You don't know.
Gotta make a site visit.
Yeah, that would be a good idea. Yeah, wear your thermal underwear. And maybe a steel jacket or some sort too. I don't know. Sally?
Are the planets all on alignment with the equator, or do they?
Generally, yes. The solar disk is generally a flat disk. I'm not saying it's perfectly flat, but yeah, they are all pretty much in an alignment. Yes. Yeah.
Well, thank you, John. I also want to thank Tyler and Adam for recording the session, and it will be on the internet. It is on the internet now, I guess, but
Is it?
it's
Oh.
already edited.
Okay.
And the next one will be as well, and I believe we'll put the slides up there.
Yes.
Yeah, so the
Yeah.
slides will be on the North Shore Amateur Radio Club site. So, thank you very much.
Okay. Thank you. All right. There's no exam.